Tseung self-powered F.L.E.E.T generator. The F.L.E.E.T, forever lead-out existing energy transformer, device is a self-powered electrical generator which has no moving parts and which can be constructed cheaply. It has been developed by a Hong Kong-based team of people, Mr. Lawrence Tseung, Dr. Raymond Ting, Miss Forever Yuan, Mr. Miller Tong and Mr. Chung Yi Cheng. It is the result of some years of thought, research and testing, and it has now reached an advanced stage of testing and demonstration and is nearly ready for commercial production. Mr. Tseung has applied his lead-out theory to the category of low-power circuits known as the F.L.E.E.T circuits. These circuits originated with an article by Mr. Z. Kaparnik, in the Ingenuity Unlimited section of the November 1999 edition of the Everyday Practical Electronics magazine. The initial circuit allowed the very last energy to be drawn from any ordinary dry cell battery, and used to light a white light-emitting diode, LED, for use as a small torch. It allows a battery which is considered to be fully discharged, to drive the circuit until the battery voltage drops right down to 0.35 volts. The initial circuit uses a bifilar coil wound on a ferrite ring or toroid. Bifilar means that the coil is wound with two separate strands of wire side by side, so that each adjacent turn is part of the other coil. A coil of that type has unusual magnetic properties. The F.L.E.E.T circuit is like this. It is important to notice how the coil is wound and how it is connected. It is called a toroid because it is wound on a ring. The ring is made of ferrite because that material can operate at high frequencies and the circuit switches on and off about 50,000 times per second, 50 kHz. Notice that while the wires are wound side by side, the start of the red wire is connected to the end of the green wire. It is that connection which makes it a bifilar coil instead of just a two-strand coil. This F.L.E.E.T circuit was then adapted by Bill Sherman and used to charge a second battery as well as lighting the light-emitting diode. This was achieved by adding just one more component, a diode. The diode used was a 1N4005 type because that was to hand at the time, but Bill suggests that the circuit would work better with a very fast-acting Schottky type diode, perhaps a 1N5819G type. The circuit produced by Bill is: when driven by a 1.5 single-cell battery, this circuit produces about 50 volts with no load and can supply 9.3 milliamps of current when the output is short-circuited. This means that you could charge a 6-volt battery using a 1.5-volt battery. Gadget Mall of the www.overunity.com F.L.E.E.T forum has taken the circuit further and found a very interesting situation. He has modified the circuit and used a supercapacitor. This is his circuit. He has added an additional winding to his 1-inch, 25 mm, diameter ferrite toroid, and he uses that to power a 1-watt LED. Why he has done this is not immediately clear to me, except possibly, that it shows when the circuit is operating. He runs the circuit driven by a small rechargeable battery, which feeds 13 milliamps into the circuit, for a period of 14 hours. At the end of that time, the capacitor has gathered enough energy to fully recharge the driving battery in a minute or two, and then power a heater winding of nichrome wire, as used in mains-powered radiant heaters, for 4.5 minutes. Alternatively, that amount of extra power could boil a kettle of water. The really interesting thing about this is that the driving battery gets recharged every time, and so the circuit is self-sustaining, although it is not a powerful circuit. However, Gina has developed the circuit significantly, as she shows in her series of videos. YouTube.com. Her main point is that using the collector of the transistor as the power take-off point of the circuit is inefficient, as that draws a lot of input current without a corresponding increase in output current. She adds a 74-turn secondary winding on top of her two 11-turn F.L.E.E.T bifilar windings, and that appears to give a far better power output. She uses the very small AAA size 12V battery and further drops the output, because the light is too blinding, by putting a resistor in series with the battery and using many LEDs in series. She has recorded the following results. With no resistor, The output voltage is 58 V peaks at 62.5 kHz, open circuit output, with no load at all. With a 10 ohm resistor, the output voltage is 49 V peaks at 68 kHz. With a 33 ohm resistor, the output voltage is 25 V at 125 kHz. Leadmotor states that Gina also produced a F.L.E.E.T circuit which could light a 15-watt straight fluorescent tube for about 5 hours when being driven by a single AA battery. He states that he was not satisfied with that level of lighting, and at youtube.com he shows a version, which he thinks is Gina's design and which Gina thinks is his design, driving a 10-watt compact fluorescent light which has had the ballast circuitry removed. The build uses an expensive 3.25-inch, 83mm, outer diameter ferrite toroid, and the lighting from a single AA battery looks like this. The ferrite ring is wound like this. 13 turns of 0.511 diameter wire, AWG number 24. 3 turns of 0.511 diameter wire, AWG number 24. 300 turns of 0.255 diameter wire, AWG number 30. The main winding is 300 turns of AWG number 30 enameled copper wire with a diameter of 0.255 mm. Please notice the gap between the ends of that winding. That gap is important as high voltage is developed between the two ends of the winding, and if the winding were continued all the way round the toroid, then the insulating enamel coating the wire would be liable to burn out due to the very high voltage difference between the first and last turns, causing a short circuit. The two other windings are with AWG number 24 enameled copper wire which has a diameter of 0.511 mm, and those two windings are positioned closely side by side in the middle of the gap between the ends of the 300 turn winding. The circuit is like this. The optional 25 ohm wire wound variable resistor wastes power but creates a voltage drop across it, reducing the voltage reaching the circuit and so, dimming the light progressively, all the way down to 0. The base resistor R has been set at 22 ohms by Leadmotor, who says that it really should be 100 ohms, but he has lowered it to get brighter lighting. Please note which side of the 3-turn and 13-turn windings are connected in the circuit, as the direction of winds is very important for those two windings. It is not uncommon for people to comment on the faint whistling sound made by a F.L.E.E.T circuit, especially a low voltage version like this. It is my experience that the sound is caused by the transistor resonating with the frequency of oscillation of the circuit, the TIP3055 being particularly prone to this. I suggest therefore, that bolting on a heatsink, which is most definitely not needed to dissipate heat produced by the circuit, will alter the resonant frequency of the transistor/heatsink combination and so stop the whistling. Mr. Lawrence Tseung has taken the F.L.E.E.T circuit and modified it to become a circuit with a very serious output, moving it into a completely different category. As a first step towards what the team calls their F.L.E.E.T device, the toroid has been enlarged to a much greater diameter. The coil is now wound on a section of plastic pipe, 170 mm, 6.5 inches, in diameter and 45 mm, 1.75 inch, deep. This section of pipe is bifilar wound with two wires side by side as already described for the F.L.E.E.T construction. As before, the start of one wire is connected to the end of the other wire. Then, the winding is given a layer of electrical tape to hold it in place and to provide an easy working surface for a second winding. The wire used for the winding is the widely available red and black pair of wires, sometimes called figure of 8. Because the cut end of the wires looks like the numeral 8. The wire should be able to carry 2.5 amps. It must be side-by-side wire and not one of the twisted varieties. It looks like this. The second winding is made in the same way, but the connections are slightly different. As before, the end of the first wire is connected to the start of the second wire, but that connection is then insulated and not used in the following circuitry. This just connects the two windings one after the other, known technically as being connected in series, and is the equivalent of making the winding with just a single strand of wire. The completed coil may look like this. This particular design is still in its early stages, and so many different coil sizes and constructions are being tested. The arrangement is for the inner winding of the toroid to be oscillated by the F.L.E.E.T circuit already described. This causes a pulsating magnetic field to envelope the outer winding of the toroid, producing an electrical output, which is capable of doing useful work. The really important thing about this arrangement is the fact that the amount of power coming out of the circuit is very much greater than the amount of power needed to make the circuit operate. The additional power is led out of the local environment and drawn into the circuit, becoming available to do useful work. The overall circuit then looks like this. While the outer winding is shown here with thicker wire of a different color, this is only to make the arrangement easier to understand. In reality, the outer winding is with exactly the same wire as the inner winding, and it will normally go all the way around the toroid. The total amount of wire needed to make the windings is about 70 meters, and so it is normal to buy a full 100-meter reel of the twin-core wire, which allows both windings to be made and leaves spare wire for other things. For those of you who are very technically minded, the output waveform looks like this. And the voltage pulses in this output are occurring about 290,000 times per second. What has worked better for me is using a bridge of 4 diodes rather than a single diode. I have used this circuit, driven by a 1.5 volt battery, to charge 12 volt batteries, but the best results are in the 5 to 6 volt range. I have used this circuit to confirm coefficient of performance greater than 1 by charging one small 12 volt lead acid battery with an identical battery, swapping the batteries over and repeating the process several times. The result was that both batteries gained genuine, usable power. I suspect that the effect would have been much greater if I had charged 2 or more batteries in parallel. The toroid was an 8-inch diameter, 10 mm by 12 mm offcut from a plastic pipe which happened to be to hand, and the wire used was plastic covered 6 amp equipment wire, again, because it was to hand at the time. Winding the toroid and setting up the circuit was done in a single evening. Overall, this is a very simple, cheap and easily constructed coefficient of performance greater than 10 device which has the potential of providing large amounts of free, usable, electrical power. With further development, it may well be possible to produce a version which could deliver the power needed by a whole household. It is also likely that these devices will become available for purchase at quite a low cost. All in all, this is a very important device, and full credit must go to the development team who have carried the research to this point and who are continuing to refine the design to produce more and more power. There are various circuits which I have shown which use the well-known F.L.E.E.T circuit as part of the design. These devices have worked well for me. However, in 2014, Tsukuhio stated that some people found that pulse charging batteries for a few times caused those batteries to then have surface charge where the battery voltage rose without there being a corresponding genuine charge inside the battery. That is something which I have never experienced myself, but that might be because I didn't discharge and recharge batteries a sufficient number of times for me to experience the effect. Tsukuhio uses this circuit. That circuit looks rather complicated with 2 of the transistors connected upside down and protection diodes connected between transistor collector and base. Tsukuhio says that he has used this circuit for 4 years now, without experiencing any surface charge effects. My preferred form of F.L.E.E.T uses a bifilar coil of 0.335 mm diameter wire wound on a paper cylinder formed around a pencil and only 100 mm, 4 inches, long, as that produces a very cheap and lightweight circuit. As I understand it, the F.L.E.E.T produces a rapid stream of high voltage spikes of very short duration. Those spikes cause the local environment to feed static energy into both the circuit and the circuit's load device, typically an LED or a battery. While I have never experienced surface charge from a F.L.E.E.T circuit, I tested some old Digimax 2850 mAh test batteries which had been sitting unused for more than a year. These did indeed show a surface charge effect when load tested. The first test used 1 battery to drive the circuit and charged 3 batteries in series using this circuit. but no matter how long the circuit operated, it would not charge the output battery above 4.0 volts, which is 1.33 volts per battery. The load test results were terrible, with the voltages at 1 hourly intervals being 3.93 volts, 3.89 volts, 3.84 volts, 3.82 volts and 3.79 volts after only 5 hours of powering the load. That is ridiculous performance, as those batteries managed 22 hours of load powering with the solar panel design. Perhaps the batteries were damaged. So I overcharged them with a main operated charger, reaching 4.26 volts, which is 1.42 volts per battery, and the hourly load testing results were 4.21, 4.18, 4.16, 4.15, 4.13, 4.12, 4.10, 4.08, 4.07, 4.07, 4.06, 4.05, 4.03, 4.03, 4.02, 4.01, 4.00, after 17 hours, 3.99, 3.99, 3.98, 3.97, 3.97, 3.96, 3.96, 3.95 after 25 hours, and 3.90 after 33 hours. Clearly, there is nothing wrong with the batteries, so the effect must be a factor of the charging. Feeding static electricity into a capacitor converts it into normal hot electricity, but we want a very simple circuit, so the next step was to add in a 100 volt 1 microfarad capacitor, which looks like this. Making the circuit. With the battery on charge removed, the voltage on the capacitor reaches 22 volts. Charging the same batteries with this circuit reached 4.14 volts and produced load results of 4.09, 4.05, 4.01, 3.98, 3.96, 3.93, 3.90, 3.88, 3.85, 3.83, 3.81 and 3.79 volts after 12 hours, which is much better than the 5-hour total previously experienced. However, obviously, something better is needed. The next step is to use a diode bridge of 1N4148 diodes instead of the single diode, giving this circuit. Without the charging battery connected, this circuit gives 28 volts on the capacitor and the battery charging is good, giving load testing results of 4.18, 4.16, 4.15, 4.13, 4.11, 4.10, 4.08, 4.08, 4.06, 4.05, 4.04, 4.03, 4.02, 4.00, 3.99, 3.98, 3.97, 3.96, 3.95, 3.95, 3.94, 3.94, 3.93, 3.93, and 3.93 volts after powering the load for 24 hours. This seems to be a very satisfactory result for such a minor alteration. If two 1.2 volt batteries are used to drive the circuit, without a battery on charge, then the voltage on the capacitor reaches 67 volts, but that is not necessary for charging a 12 volt battery. Although the change is slight, the circuit operation is changed considerably. The capacitor does not discharge instantly, and so, for some of the time between the sharp F.L.E.E.T pulses, the capacitor supplies extra charging current to the battery on charge. This does not mean that the battery being charged is charged much faster, and you can expect that full charging will take several hours. I have not yet tested it, but I would expect that by using 2 or more of these circuits simultaneously, should increase the rate of charge. There is no need to restrict the battery on charge to a nominal 3.6 volts in any of these circuits, as a single 1.2 volt drive battery can easily charge a 4.8 volt battery or larger. The value of the capacitor has a considerable effect. And I suggest a 1 microfarad capacitor is a good choice. It has been argued that the 2 additional diodes on each side of the battery being charged are not necessary, although I have shown them to isolate the 2 circuits from each other.